Okay, so we are looking at the rubber ducky problem, problem number 14 of the wave optics intergalactic. Ernie is hanging out with rubber ducky in the bathtub, and notices that in his bubble bath, there's a soap bubble floating around. And Ernie, being the brilliant physicist that he is, he starts asking himself what would be the thinnest soap bubble possible that could exist that would appear black or dark or at a minima if it was illuminated by light of a wavelength of 480 nanometers. So there's our monochromatic coherent light, which we need. And this is a thin film problem because we're looking for the thinnest soap bubble. So let's draw this out. You have to draw these out for the thin film problems. If you're not doing this, you're probably going to get them wrong. It's just how to do them. So we've got our thin film right here. This is the bubble, right? And let's put our three indexes. We've got N1 equals 1 because we're in the air. N2, which is the bubble, is 1.42. Ernie remembered that for us. And N3 is whatever substance is on the inside of the bubble. And the really cool thing about that is the inside of the bubble has air, once again. So as we bring the light down, and remember, this light is technically coming down and then going back up and then going through and then going back up. That looks really dumb drawing it that way. So we tend to draw it at a slight angle so that we can see these reflections. We get some light that immediately reflects off. This is our reflected path. We could call this right here some delta A, which we'll look at in a second. And then some of the light is transmitted into the soap bubble. There is a reflection on the back side here, but that bubble, this light here, this wave, also comes out and then continues to go. So we actually have two things going on here for path length delta B. We have the thickness of the bubble it's going through twice, so there's twice the thickness, and then there's the reflection. If we have a hard reflection, hard reflections cause a phase change to occur within our wave. They cause phase changes of 180 degrees, also referred to as half of a wavelength. A full wavelength from start to finish is 360 degrees. It's like going around the circle. If we go halfway on the circle, that's 180 degrees, or lambda over 2. A soft reflection does nothing. It gives no phase change, 0 degrees, no change. So let's ask ourselves what's going on with delta A and delta B. So delta A goes from a low index to a high index, and we know that when we go from low to high, we are going to get a hard reflection. So we're going to get a lambda over 2 shift for delta A. For delta B, we are going from high, because we're in the N2, we're in the bubble, and we're going to low, and when that occurs, we get a soft reflection here. So we add nothing to delta B. It is totally fine as 2t. So at this point, we've kind of drawn our picture. We've got good ideas of delta A, delta B. We just need to subtract them. So it's delta B minus delta A. We're just going to get 2t minus lambda over 2. And Ernie here is looking for a minima. He's looking to make a dark bubble. And we think about these thin films the same way we think about double slits. Minima happen at half integer values of the wavelength. So lambda over 2, 3 lambda over 2, 5 lambda over 2. So if we have m plus lambda over 2, or rather m plus, we could write it like this, m plus 1/2 lambda, it's a better way of writing that. We just need to make the thinnest soap bubble possible. Normally when we do this, we ask ourselves the question, what's the smallest value of m that could exist here and not completely wipe out our problem? Because sometimes if we set the value of m equal to 0, then the thickness has to be 0. So what happens in this case if we set m equal to 0? Well, if m equals 0, we still have some wavelength left over, and we're going to be fine. So let's set m equal to 0 here. And in doing so, we get 2t minus lambda over 2 equals lambda over 2. Then we could add a wavelength over, so adding a lambda over 2 over to the other side, Whooshing! Lambda over 2 plus lambda over 2 just gives us lambda. So we get 2t equals lambda, and then we simply divide by the value of 2. This gives us one of our two possible answers here. We know it's either going to be lambda over 4 or lambda over 2. Turns out in this problem, for the minimum thickness to make a dark bubble, we get lambda over 2. And then here's where you need to be a little bit careful. This is where everybody makes a mistake. A lot of people just say, oh, I'll put the 480 nanometers into here. I'm done. But they're not. You're not done at all. What you should be saying is, look at this. This lambda is the lambda in the second medium. I don't know why I'm making a weird voice, but I am. And what this means is that if you're in the medium, you need to switch your wavelength. Your wavelength in that medium, the bubble, is going to be equal to your proper wavelength. That's your wavelength in a vacuum, the 480 nanometers, divided by the index of refraction in that medium, in the bubble. So in our case here, we could write this as wavelength proper divided by 2 and 2. And to give Ernie a number, we find the thickness is equal to 480 nanometers divided by the quantity 2 times 1.4, what was it, 1.48? 1.42. And if we run this calculation real quick, we get something around 158 nanometers. Waching! There we go, Ernie. Congratulations. I hope you had fun with the rubber ducky. That's that problem for a thin film. Hope you enjoyed it.